Assalamu alaikum. Dear students, today we will learn the boost converter. Boost converter is also a DC-DC converter. It is different than the buck converter in a way that the buck converter basically steps down a higher DC voltage level to a lower DC voltage level, while the boost converter steps a lower DC voltage up to a higher DC voltage level. So it's basically improves the output voltage. So the output voltage is more than the input voltage. So as we did some assumptions in the buck converter, so I want to just ensure you that those assumptions that were considered true for the buck converter are also assumed true for the boost converter. For example, we assume that the switches are ideal. They basically they do not consume any power during their switching operation. When the switch is closed, the voltage across the switch is zero, hence the power consumed is zero. Similarly, when the switch is open, the current through the switch is zero, and hence the power consumed by the switch is zero. So we are considering that all the components are ideal. The switches don't consume any power while performing the switching operation. The inductor current is basically always positive. That is, the boost converter is also working in its continuous conduction mode. The average voltage of an inductor is zero. Similarly, average current through a capacitor is zero, and the output voltage is constant since the capacitor is large enough to maintain a constant voltage, or we can say a considerably small ripples are there, so we can ignore them. So these were the assumptions that we did while performing the derivations of the buck converter. So they are also true for the boost converter as well. Now, similarly, we assumed that the switch will be closed for the time dt, and it will be open for the time 1 minus d times the capital T, that is the time period of the uh, switching cycle. So these assumptions are also true. So as I already told you about the positive inductor current, and the capacitor is very large so that the output voltage is considerably held constant, and the components are ideal. So now coming to the figure that is being displayed here, the top figure is basically the figure where we have basically shown everything to you, that the switch is there which can be closed or which can be opened. There is a diode. uh, if you compare this circuit diagram with the circuit diagram of the buck converter, so you will see that uh, the switch was in place of inductor there, and the diode was in place of the switch there in the buck converter. So what happens that when we change these positions, then the output voltages and the output currents basically differ from the previous configuration. Uh, I most often tell my students that one of the greatest grandmasters, uh, basically, when he was interviewed, he said moves are not important. So everybody was surprised that the grandmaster is saying that moves are not important. But the second sentence was the order of moves is important. So similarly, in electrical engineering, what happens that uh, if we change the order of our components, if we change the switching pattern, we can often achieve uh, things that are beyond the imagination of a layman or a common man. So here what happens that when we change these things and then we basically close the switch, so you will basically get this B figure. And now if we apply KVL on the left loop, we can write minus Vs plus VL equals to 0. And hence we can say that basically VL equals to minus Vs when the switch is closed. Similarly, if the switch is open, then what happens that we get this figure C. And for this figure C, if we apply KVL on the outer loop, we can say that Vs is equals to minus Vs plus VL plus V out equals to 0. And hence we can say that VL equals to Vs minus V out. So now we will follow the same pattern which was followed in the buck converter, that if the output voltage is also if the load voltage VL, inductor voltage VL is equals to Vs, then inductor voltage is L di by dt. So we can write di by dt as Vs upon L. And since the di is representing change in the inductor current, so we can write di as delta IL. And since dt is change in inductor, since dt is basically change, uh, basically the duration for which the switch was closed, so it was dt. So hence we can write delta IL upon dt equals to Vs upon L, and hence delta IL closed is basically Vs dt upon L. Now similarly, uh, for the switch is open, what we can say that VL, that is the inductor voltage, is Vs minus V out. Now since the inductor voltage is L di by dt, following the same pattern, DIL is basically delta IL, and dt is basically the time for which the switch is open. And this time the switch was open for 1 minus d times capital T. So hence we can say that Vs minus V out upon L is equals to delta IL upon 1 minus d into T. Now from this equation we can easily conclude that delta IL open is basically Vs minus V out multiplied by 1 minus d into T whole divided by L. So as you remember that when we calculated the values of delta IL open and delta IL closed, what we did next was basically we took the sum of these two delta IL, and since they are cancelling each other, so the sum is equals to 0. So following the same pattern, we basically added delta IL closed and delta IL open, and we got an expression. And if we make V out subject from this expression, we will get it as Vs upon 1 minus d. Now consider this equation 6.27. It is very interesting situation. If we take d equals to 0.5, what happens that output voltage becomes V out equals to Vs upon 1 minus zero point 0.5, that is Vs upon 0.5, which means that output voltage V out is equals to 2Vs. So we can say that the output voltage is double than the input or the supply voltage Vs. So hence we conclude that if D is zero point 0.5, then the output voltage is double than the input voltage, and hence we can say that the configuration is basically improving the output voltage. Output voltage is more than the input voltage, and that is the thing that we name it as the boost converter, because the output voltage is boosted from Vs to 2Vs. So now they are saying that the same output voltage expression can also be achieved if we consider the inductor voltage. The inductor voltage was Vs when the switch was closed. So Vs into dt plus the inductor voltage was Vs minus V out when the time was 1 minus d into t. So The inductor voltage is basically Vs minus V out into 1 minus d into T. Now in these two terms, uh, T is not written because we can take it common and uh, bring it towards the other side and it will become 0. But the conclusion is that from this equation, again, if we make V out the subject of the equation, we will get equation 6.27. So in a number of ways, we can prove that for the boost converter, the output voltage V out is Vs upon 1 minus T. Now, what is the output power? It's very simple. We can represent output power by V square upon R. So if the output voltage is V out and the output current is I out, then we can easily say that P out is V out times I out. Similarly, if we put the value of IL there, so we get V out Vs into IL equals to Vs square upon 1 minus d square into R. And hence, IL is equals to V out into I out upon Vs as represented by equation 6.28. Now to form the equation of I maximum, form the expression of I maximum, what we will do, uh, we will follow the same pattern that we followed in the buck converter. That is I maximum is basically IL plus delta IL upon 2. So here delta IL upon 2 is basically Vs dt upon 2L and IL equals to Vs upon 1 minus d whole square multiplied by R. So using this expression, we basically established I maximum and I minimum equations. Now, again, since the boost converter is also operating in the continuous conduction mode, we will take I minimum equals to 0 and hence we will find the minimum value of inductance that is required for the continuous current operation. So this is represented by equation 6.32. Now again, as in the buck converter, what we did, basically we considered the output ripple voltage and hence we established the equation of the capacitance that is required to maintain a minimum percentage ripple. So following the same pattern, uh, we we wrote basically delta Q equals to V out upon R times dt. And uh, again, as we know that Q equals to CV, so making that delta Q equals to delta V into C, we basically made delta V the subject of the equation and we got delta V naught equals to V naught upon V naught D upon RCF, and delta V naught upon V naught is basically the percentage ripple. So this is equals to D upon RCF. Now from this equation, that is equation 6.34, if we make C the subject of the equation, we get equation 6.35, and it is basically the capacitance which is required to maintain an appropriate delta V naught upon V naught, that is an appropriate percentage ripple. Now at the end, uh, we will consider the ripple voltage due to the equivalent series resistance of the capacitance, and as in uh, the buck converter, it is again represented by delta IC into RC, or what we can say, delta V naught due to ESR is equals to uh, IL maximum time RC. So that was all about the boost converter. So inshallah, in the next class, what we will do, we will perform some uh, numericals related to the boost converter and we will discuss the design consideration of the boost converter. So inshallah, we will meet you in the next class. Till then, take care and Allah Hafiz. Thank you.